Section 2.7, linear programming. This isn't something that is terribly new. We actually talked about this, and I mentioned this in section 2.6. We're kind of applying what we did in 2.6 into something that's real life. We're kind of extending that idea of maximum and minimum values to now it's something a little more formalized. In section 2.6, you were given a function, you were given a system of inequalities. You needed to find the vertices and find which one gives you the maximum, which one gives you the minimum. We're going to do a lot of the same thing in this section, but now you're not going to be given hardly anything. You're going to be given the information, and it's going to be up to you to come up with the system of inequalities. It's going to be up to you to find the equation in two variables that we need to either maximize or minimize. But these really aren't that difficult. The examples here I've got, I'll walk you through them. I've got two examples, and then that'll be all. So linear programming is a vocabulary term. Linear programming is a procedure for finding the maximum or minimum value of a function in two variables subject to given constraints. Now, constraints is another vocabulary term. Constraints are simply conditions given to variables. Like in the one-story problem in section 2.6, it was about the number of pounds of butter in a batch, or the number of tins of cookies that they could produce in a day. Those are constraints. Okay, so the procedure for linear programming, you can see them there. Step number one, we got to define the variables. What does X represent? What does Y represent? Step number two, then write your constraints as a system of inequalities. You might have two, you might have three, you might have five. It's really going to depend on the situation. Number three, graph the system and find the coordinates of the polygon. I'm okay with you using technology here. Use Desmos to find your information, your vertices that we need to test. Step number four, write the expression. That will be given to you. The information will be given to you in the setup to the equation or the setup to the problem. It's going to be up to you to find and write the equation or the expression. Step five, then substitute, figure out, and then step six, which one gives you the biggest or the least, depending on what you're being asked to do. So, I got a story problem here. It takes a minute to write it all, get it all written up and written down. So, if you want to pause the video here, I'm not going to read it to you. Just pause the video, and then we'll go from there. When you get it done, start the video, and we'll get started again. All right, this problem here talks about maximizing profit. So anything you see in the setup that talks about profit. So we got this $8 on sets. We've got $2 on cassettes, on single cassettes. That's stuff we don't need to worry about right now. That's what we're going to use to figure out what we're going to maximize or minimize later once we get it graphed and find our vertices. We're not going to pay attention to that stuff right now. What we need to do first, and we need to let's just follow our steps. Define the variables. So, to me, I think X should be the number of sets that is produced. Number of sets, and then Y is going to be the number of singles. Okay, so there's step number one. Define the variable. Step number two, write the constraints as a system of inequalities. Well, what does it tell us that we can do? Well, it talks about how long it takes to produce a set, how long it takes to produce a set, how long for a single, how long machine A is running, how long machine B is running. It says we can produce sets and singles on both machine A and machine B. So let's talk about machine A. So machine A, we know that it takes 9 minutes for a set on machine A, so 9x. Singles are 1 minute. It says it right there. So it'll be 9x plus y, because we're talking about total amount of time that the machine is running. So it says the machine A is run for 54 minutes. Now, we can't go over that, but we could have less than that. So we'll have less than or equal to 54. Okay? Machine B. Let's talk about machine B. Machine B says it takes 3 minutes for a set. So that's going to be, whoops, go back to the pen. 3x, again, 1 minute for a single on machine B, so plus 1y, and it says machine B runs for 42 minutes, so we're going to say less than or equal to 42. Really, these are pretty much the only two constraints that we have. If you want to add a third and a fourth, it is possible, or it might be necessary when we're defining our polygon. What we could talk about is the number of sets and the number of singles. We know for sets, we'll do this in orange, the number of sets, we can't produce a negative number of sets. So we could say X has to be greater than or equal to 0. And then we could say the same thing with the number of singles. And I'm running out of colors here. We'll go to brown. So the singles here, the singles, those are the y values. Those can't be negative. So y has to be greater than or equal to 0. So now we've got we've got enough information here that we've got our system, we've got our constraints. Now let's go ahead and graph it. I already used Desmos for this, and this is what the picture looks like. Now the colors are a little bit different than what I wrote them in, but that's okay. So this one, the y-axis is the x is greater than or equal to 0. The x-axis is y is greater than or equal to 0. The flatter line here is the 3x plus y is less than or equal to 42. The steeper line is 9x plus y is less than or equal to 54. And our polygon, where all the shaded areas overlap, is right here. So there's one side, here's another, here's a third, and here is our fourth side of our polygon. So this is all the possible combinations or possible solutions to our system of inequalities. Now we need to figure out what the vertices are. Again, you can just tap on this if you're doing with your phone or with a tablet, or just click with your computer, and it will tell you what these points are. This point right here is it's 236. This point up here is 042. This point down here, you can see it on the graph, is 60. And then this point, you can also see that one on the graph. That's going to be the origin, 0, 0. So those are our four possible outcomes that could potentially maximize our profit. Now we need to talk about profit. If I go back to this screen here, we can talk about profit. Profit on each set is $8, and the profit on each single is $2. And we want to maximize the profit. Well, let me switch back to green here. I'm going to slide this up. Our profit, we can say P of XY, P standing for profit, because we're writing a two-variable equation here. We know it's $8 profit for a set plus $2 for a single. Okay, and we have four possible options, four possible outcomes that we need to test. So we're going to go ahead and test all of them. So P of, let's start with 0, 0. If we produce 0 sets and 0 cassettes, I'm pretty sure you can see where this is headed. If we produce nothing, we're going to make nothing. So 8 times 0 plus 2 times 0, that's 0. That's not going to maximize our profit. That's pretty obvious. But the other ones, we need to think about the other possible outcomes here. So if we look at 6, 0, so let's take 8 times 6 plus 2 times 0. 8 times 6 is 48. 2 times 0 is still 0. So this is going to be $48. If we produce 6 sets between the two machines, we're going to make $48. Okay? If we try one of the other 2 points, let's try 042. If we produce no sets and 42 cassettes in our time frame here, we're going to take 8 times 0 plus 2, whoops, let's make that a little better, 2 times 42. 2 times 42 is 84. 8 times 0 is 0, so this is going to be $84. And then we have that final point, which was 236. So P of 2 comma 36. We're going to take 8 times 2 plus 2 times 36. 2 times 36 is 72. 8 times 2 is 16. 16 plus 72 is 88. So the question is, which one is the highest? Well, 88 gives us our highest profit. So to answer the question, which was determine the number of sets and singles that maximizes profit, well, we should produce, or we should manufacture, should produce 2 sets and 36 singles. And that would be our answer, 2 sets and 36 singles. There are times when you won't have an answer. Okay, this example did have an answer, but sometimes they won't. And when that happens, the situation is called infeasible. An infeasible problem is a problem in which all the constraints cannot be satisfied, meaning no polygon can be formed in quadrant 1. There's a picture in your textbook, I don't remember the page number off the top of my head, that would show you, or that shows you what an infeasible situation looks like, but basically there's no polygon in quadrant 1, and if there's no polygon in quadrant 1, it's not going to work. Remember, quadrant 1 is important here because usually X and Y represent objects or time or people. You can't have negative of any of that, so everything has to be positive here. So we don't have to if we don't have a polygon in quadrant 1, then it'd be a situation where it is infeasible. Now, it could also be that if you don't have a solution, that your situation is unbounded. Now, unbounded means all constraints are satisfied. There's a double shaded area or a common shaded area wherever all the constraints are satisfied, but there's no optimal solution. Something that would be unbounded could look like this. So we have an x and y axis. We have our two curves. We have a red one. We have a blue one. And the problem is our shaded area could be something like this. It'd be right in here. There's no area back on this side of it that kind of closes it off. And that does happen every once in a while. Now, this would be an example where we do have a minimum value. We would have a minimum point right in here, okay? But there's no maximum. We could say a minimum exists. A minimum exists, but there's no max. There is no max. And that would be an example of an unbounded situation. The constraints are all satisfied. All of your possible outcomes are in here, but there's no one that optimizes or maximizes your situation. There might be one that minimizes it, but it's not maximized. And that's what unbounded looks like. You could have a situation where there are more than one optimal solutions, and that's called alternate optimal solutions, a problem that has two or more solutions that provide an optimal output. And I've got an example of that right here. So a manufacturer makes widgets and gadgets. You can read the constraints from there. Again, if you want to read it to yourself, write it down, pause it, go ahead, and we'll pick it right back up. All right, let's start by defining our variables. Remember, step one is to define the variables. So let's say x is equal to the number of, it starts with widgets, so we'll talk about widgets first. So x is the number of widgets, which then means y should be the number of gadgets. Okay, so there's our definition of variables. Now let's talk about the constraints that we are under. We need to make at least 500 widgets and 700 gadgets. So there's a couple of inequalities that we can write right there. So we can say the minimum widget, we could say is x is greater than or equal to 500. We need at least 500 to meet the minimum daily demands. We does say something as well also about minimum gadgets. It's right there, 700. So we could say minimum gadget, and that would be y is greater than or equal to 700. We need to produce at least 700 to meet daily demands. It also says machinery can produce no more than 1,200 widgets and 1,400 gadgets. So we do have maximums on those. So max widgets would have to be x is less than or equal to 1,200. And then the max gadget is going to be y is less than or equal to 1,400, because it says 1,200 widgets, 1,400 gadgets is the maximum. It can produce no more. What else does it tell us? Well, it says combined number of widgets and gadgets that the packaging department can handle is 2,300 per day. So if I take, we'll just call this packaging, we can say the number of widgets plus the number of gadgets, because it says the combined number can handle is 2,300 a day, can handle no more than that. So it's got to be less than or equal to 2,300. And I'd say that's about it, because it's asking about maximizing profit, and this is a price. So we don't need to worry about that right now. I would say this right here is our system. We have 5 inequalities that we need to graph. Now these are going to be big numbers, 500 and 700 for our minimums, 12 and 1,400 for our maximums, and then this is a line with 2,300 as a y-intercept. Again, use Desmos, use a graphing calculator, use technology to your advantage to graph this. I already did that, and it looks like this. Okay, your polygon here, so let me just kind of point things out. This is y is greater than or equal to 700. This is y is less than or equal to 1,400. This is x is greater than or equal to 500. X is less than or equal to 1,200. And then here is the x plus y is less than or equal to 2,300. Your common shaded area is this polygon right in here. Okay, there is your polygon. We have 5 sides, which means we have 5 vertices. This one right up in here is, let's see, it looks like 900, 1,400. 900, 1,400. This point right here is going to be 1,200 comma 1100, 1200, 1100. This point down here is 1200, 700. This point right here is 500, 700. 500, comma 700. And then this point up in here is going to be 500, 1400. So 500, 1400 for that point in the upper left. So we have 5 points that we need to talk about. Now we need to figure out what our profit is going to look like. What is our profit equation going to be? Well, it says that they sell each, the widgets and gadgets, both of them are sold for $1.59 a piece. So the profit of X comma Y is equal to, well, we're going to charge $1.59 for each widget, and we're also going to charge $1.59 for each gadget. So 1.59Y. That's it. That's our profit equation. Now we have to check which one of these 5 points gives us the maximum profit, and this is going to be calculator work. I did it in the calculator. I'm not saying you shouldn't. Use the technology that is available to you. So profit of, let's start with the, let's just start here, and we'll start down here at the lower left, and we'll work clockwise. We'll just go around the clock this way. So 500, 700 is going to be first. 500, 700. So we're going to go 159 times 500 plus 159 times 700. And if we make 500, if we just do the minimum, what we're going to get is a profit of $1,908. And like I said, we're just going to keep working our way around the polygon here, and we're going to go clockwise. So next one's going to be 500, 1400. So profit when we produce 500 widgets and 1400 gadgets, it's going to be 159 times 500 plus 159 times 1400, and when we do that, we get a profit of $3,021. Okay, next up would be 900, 1400. So profit when we produce 900 widgets and 1400 gadgets, so $1.59 times 900 plus $1.59 times 1400. And that would be a profit of $3,657. And then what's next? So that's the third one. 1200, 1100 is next. So profit 1200 widgets, 1100 gadgets. So $1.59 times 1200 plus $1.59 times 1100. And that is also a profit of $3,657. And then we have a fifth option that was 1200, 700. So profit of 1200, 700. So 1200 widgets, 700 gadgets. So $1.59 times 1200 plus $1.59 times 700. And that one gives us a profit of $3,021 again. So which one gives us a maximum profit? Well, we actually have two different possible combinations. Okay, the 900, 1400 or 1200, 1100. So when this happens, when you have multiple optimal solutions or alternate optimal solutions, got a vocabulary term, we need to list all of them, all of the possible outcomes that maximizes the profit or maximizes the problem. So we either need to sell 1200 widgets and 1100 gadgets, or, so that was this one. So now we need to list the other one. The other one would be 900 widgets and 1400 gadgets. We need to list both. Or if there were three, we'd have to list all three. Anything that gives you a maximum profit needs to be listed, and those are your answers, plural, in this example.